Alright, so the video I'm making today is to answer the question which I keep getting asked by my friends and family, which is, what does Harry do for a living? So, I created a program that allows us to generate fractals, like the one in the picture here. So, a fractal is something that is defined as a curve or geometric figure, each part of which has the same statistical character as the whole. There's more to the definition there. That's the key part for now. So what that means here is that if you kind of zoom in on any part of a certain fractal, it'll look the same. So in the example here, we have something that's called the Sierpinski triangle, where I put a picture of it as the whole, so the outside of it, the whole, what you can see from before zooming in on it. And then I zoomed in on a part of it, which is the square here, which I believe you can see my mouse here, but I am about to zoom in on this square here, which then brings me to the picture on the top left. As you can see there, it looks the exact same. So then I zoom in a little further and I get the picture on the top right. Still the exact same. I zoom in on that tiny little square on the bottom left, and now I go to the bottom left, and here's another picture. And you can start to see here that zooming in on it, the dots are a little like the points, they're a little more spread out than they were before. So the reason behind this is that a computer, it can only generate so many points. It can't generate an infinite number of points, which is what the true form of the fractal would be. So technically this is just an approximation. It's not the whole fractal. So then lastly, I zoom in one more time and I get this picture on the bottom right where you can see it's still a triangle, but it's zoomed out, or zoomed in, sorry, and you just have three triangles that are 3 points. So let's look what's next here. How are they created? They are created using what's called an IFS, which stands for an Iterated Function System. An IFS consists of a specified number of functions that, when iterated upon a given starting point, give us our image, the fractal, which we call an attractor of the set. So let's go further into this. So for example, here we have the Sierpinski triangle, which was created with the following iterated function system, which has 3 functions. So each function we can see here starts with, and it has matrices, which I'm going to send to my friends and family who don't study math, but that's okay. So what it's doing is it's taking 0.5 of your x value and 0.5 of your y value for your first function to make a new point. For the second function, it's doing the same thing, but then it's also moving it to the right by 0.5. And then the last one, it's moving that point into the middle by 0.25 and 0.433. So what this is doing when you're doing it deterministically, when it's saying, okay, you're taking a starting point, and then you're putting that through each function, and then you're taking each of these new points that's generated, and you're putting that through each function. So you get a number to the power of 3, or no, sorry, you're getting 3 to the power of whatever number of iterations you have. So you can see here, started with a point, which I said 0, 0, put that through function 1, function 2, and function 3. Then I put each of those points through all the new functions, and so on. You'll do that forever to get the true fractal. But in the pictures I gave there, the most zoomed out one was, I believe I did that 12 times. So you could get a ton of points doing it that way. I believe when I did it that way, you get about 743,000 points. It's a ridiculous number. So, but it's not necessarily the most efficient way to calculate it, because you get a ton of overlapping points, and those points exponentially get bigger and bigger. So say if I wanted to go from 700,000 points, like I just said, and I wanted to do one more iteration, that would bring me to about 2 million points, which is a lot to handle. And then if I were to do that again, I would get a ridiculous number of points, and my computer cannot handle that. So a more efficient way that we can generate these fractals is by using what's called the chaos game. the chaos game picks these functions randomly by, instead of, say, generating 1 point and then you put that through each 3, I will just pick another one of my 3 functions randomly. And then that one will give us a new point. And then from that new point, I'll pick another function randomly. And so we're just getting all of those functions chosen with however many points we want to make. So on the right here, you can see we have the Sierpinski triangle, same as it was before, but now we're using the chaos game method. So when you're fully zoomed out, you can't even tell the difference. It looks the same. Then you zoom in a bit, and on the second image here, if you were to look really closely, you would maybe, just maybe, notice, but no. And then you zoom in one more time, and you can tell here, there's no order necessarily. It's contained within a certain spot. Like if you look on the side here, all of these points are along a line here, which is awesome. But if you zoom in on it, that doesn't always hold. So there's also other types of fractals. The ones we were just talking about, like the Sierpinski triangle, are linear. They are created using linear functions. So say you take half of a point and plus a constant value, or you take half of another point plus a constant value. But I can create other types of fractals using, say, trig functions, or functions that within a certain range are only between -1 and 1. So they're not expanding. They're just stuck within this certain area. And you get some pretty cool pictures, like some of my favorite ones, like this one on the top left. I friggin' love that one. So yeah. Now, here's something that is super cool. So we can create, well, not that stuff wasn't super cool before, but anyways, we can create subsets of these fractals by restricting the order of which the functions are chosen in. So say we have 3 functions like the Sierpinski triangle before that has f1, f2, and f3. On the right here, I have these 2 circles, which I'm going to call nodes. Well, I'm not calling them then. That's what they're called. So I can use these now to create patterns that will restrict the way functions can be chosen in. So I'm going to exit the main slideshow mode here, and I'm going to draw some stuff. So say I wanted to make something like this. I'm first going to take my first function, so function 1, and I'm going to say that function 1 keeps me at node 1. So if I'm starting at node 1 and I pick function 1, I'm staying there. Okay, so at node 1, I'm not going to include function 2, and I'll explain why in a bit. But function 3 is going to take me to node 2. So 3. Now, if function 3 were to be selected, that's going to take me to node 2. From node 2, I want something to take me back to that node 1, because if I don't, I'm just going to be stuck at node 2 forever, and it's not going to be very cool. So I'm going to say function 1 is going to take me back to node 1. And then functions 2 and 3 are both going to keep me at node 2. Like so. Cool. So what the heck does this do? So doing this, I can now say start at node 1, and from here I can pick functions 1 or function 3. Function 2 is not an option. So let's say I get function 1. Cool. I'm still at node 1, so still I can pick function 1 or function 3. So let's say next I pick function 3. And again, this is all being chosen randomly. Like function 1 could have followed itself there, could have followed itself 100 times. The odds of that happening are very small, but it could technically happen. So now I'm at function 3, where any of the functions can be chosen. If I choose function 2, you can see here that I'm still at node 2. If I choose function 3 again, you can see here I'm still at node 2. But if I were to pick function 1 here, it would take me back to node 1. And now I can't pick function 2 again. So what this is doing is it's making it so that function 2 can never follow function 1. No matter what we have, that can never happen. We can have every other possible combination except 2 cannot follow 1. So I'm going to go back to the slideshow here, and I'm going to show you that when we generate the IFS using this, we get this, where you can see the original Sierpinski triangle is in gray underneath, but we have this new subset which occupies no more than the original space, but is less. It's contained. And that's pretty cool. So that's the end of the slideshow. And now I want to show you the program I made that can do this. So here is the main interface where you start with this menu. It says, welcome to the Tiemansums Attractor generator. People who know me, which is going to be, I'm going to say 99% of the people that will watch this video, knows that my last name is Tiemann, and there's this thing called Riemann-sums, which is why I thought it'd be cool to make it and call it Tiemansums. So what you do is you start with first the number of functions in your system. So let's say here I wanted to create the Sierpinski triangle. I would put 3. Then next, I just set the bounds on my plot. So if I'm not making a morphing one, it starts with a certain shape or a certain size of the plot, and I can zoom in on that as much as I want. So setting the bounds on my plot at first doesn't necessarily matter. Next, I can choose the type of coloring I want to have with my attractor. So I can either choose to match a color to each function or to use an RGB color coding, which I can then set. I can say like base it off of the X value. I'm going to take sine of X for the R value. And doing that, you get some pretty cool color coding patterns. Like you can see here that I use the RGB color coding for these ones here, and you get this kind of smooth transition into the colors. So instead of doing that for the first one, since I've already shown you those, I'm going to match a color to each function. So I'm going to choose red, blue, and green. Next, I need to choose the type of attractor I'm going to generate. I can pick either chaos game, which is, as we explained before, was just the random points, or I can choose deterministic, which is the one before, where each point is, say, going to be take the first point, and then I generate that through each function 3 times, then each of those points through each function, and so on. And so there, I would choose the number of times I want to do that. I could say do it 2 times, where that's just going to take the first point, generate it through, you get 3 points more, and then you do it one more time, and you get each one of those is generated through the 3 functions. So for this first example here, I'm going to use the chaos game. So I'm going to say we have 200,000 points. That's the default. And then from here, I can see I have a whole bunch of different options here. I can choose a standard function, a piecewise function, splicing 2 of them together, which is where you can take 2 iterated function systems and say, okay, if a point is within a certain radius of the previous point, then I'm going to pick the one function, or otherwise I'm going to pick the other function. You get some pretty cool shapes using that splicing 2 together. I can morph IFS attractors into one another, making like a little GIF animating into each other, which is awesome. And then lastly, I have an option here for showing the language restriction process. So what you would do there is you would first take your iterated function system, and then, so from my iterated function system, that'll generate as normal. And then I would create my language restriction, and it's cool because this process would show you how that is being selected, like with the chaos game. It's pretty cool. Anyways, so I'm going to start with just a standard affine. So the non-trig function is just the linear ones, chaos game attractor, the most basic. So I'm going to press generate, and it's going to ask me if I would like each function to have an equal probability of being selected. If I were to press no here, it would bring up a submenu that would say, oh, I want function 1 to have this probability of being selected. I want function 2. I don't want that right now. I just want them each to have an equal probability of being selected. So I'm going to press yes here, and it brings me to this menu. So I just want to show you here how it works generating the Sierpinski triangle I'll get into generating other pictures too, because I want to show you something more than just the Sierpinski triangle. But, so let's look here. Before I showed you what the functions were, they were these three. So I'm going to pick this back up here, and I'm going to put in my functions. Sorry, I was kind of looking around there. I have my little microphone. I was about to pick it up, but then I just realized I don't want to hurt your ears. I have my microphone in front of my keyboard here, so it's kind of a struggle. Anyways, so I input my values here similar to how I input the functions. Or sorry, similar to how it looks down here, except it's a little less smooth. I'm not like a programmer. This is the first thing I've ever made. I'm super proud of it, but it's not the best. Anyways, so I input these functions here as they appear below. And then lastly, I'll put 0.25 and 0.433. I press next page, and it takes a little second because remember here it's generating 200,000 points, and there it is. So here, compared to the other one before, we have each one is generated with like a color matching to each function. So it's kind of cool. And you can see here, you can zoom in on it as much as you want. I could zoom in to this little square down here, and you can see because it's the chaos game, the points are all over the place. Cool. Then it asks you if you want to create a less pretty but smoother to interact with plot. If I were to press yes here, it would bring me to my browser where, as you can see, I can much quicker zoom in on it, which is awesome to have. And I can zoom out and I get this sky. So that's pretty cool. Cool. Then it asks me if I want to know the dimension of the attractor, which is just a little mathy thing. If I press yes, it would take a little bit of time, so we're not going to do that. And then it would say something around the lines of 1.54. So it would just be a little message box. So I'm going to press no for now. And it would do that no matter what you put in. And then, so as we said before, it asks if we would like to create a subset language restricted IFS of this attractor. So I'm going to say yes. So it asks you the number of nodes we want to generate. Let's go back to our picture here. So we have 2 nodes here, so that's what I'm going to put in. I'm going to put in 2. And so then from here, I can say, all right, function 1 takes me to node 1. Function 2 doesn't take me anywhere. And function 3 takes me to node 2. And each of the probability, I want them to all have equal probability too. You could mess around as long as you make sure that they add up to 1 because probability. So I'm going to say 1 over 2, 1 over 2, and 0. Then for node 2, I can see here that function 1 takes me to node 1, function 2 takes me to node 2, and function 3 takes me to node 3. I have 3 functions that are being used here, and I want them each to have the same probability. So I'm going to say 1 over 3, 1 over 3, and 1 over 3. I press next page, and it asks me if I want the IFS to appear in gray under the new LRIFS. So I showed you here how that looks. So we already know that. So I'm going to press no this time, just because I want it to look different. So I'm going to say no. That'll take a little bit of time. And then we have this guy. Can zoom in, same as before. Zoom in as much as you want. So that's pretty cool. And you can see, using the number of points, zoom in, it's using the chaos game, so it gets a little more spread out each time. Cool. And then it asks me the same thing, if I want to see the less pretty but smoother to interact with plot. This time I'm just going to say no. If I want to know the dimension, I'm going to say no. And am I finished with the program? Not yet. So next up, I want to show you how we have the non-affine attractors, so the trig functions one. So here, now I have the standard, the piecewise, the splicing, the morphing, same as before. I also have 3D attractors, which are super cool. I'll get into that in a bit. I have the 3D morphing. I have splice and morphing, Mobius morphing, which is you create these kind of transformations that are super, I don't know, they're super trippy looking. And then lastly, I can morph and Mobius morph at the same time which is super cool, and I'll show you that too after. So from here, I want to start with just the basic one. So I'm going to start with a starting point 1, 1, because I want it to be in the range of that initial function. I don't want it to mess up, because so say if I start with 0, 0, and I have a sine function there, well, it's just going to get stuck at 0 the entire time. So you need to make sure you have a function or a starting point that is in your function's range. So I'm going to press generate here, and I'm going to say yes, still I want an equal probability being selected, and it brings me to this, which is a lot more intimidating looking. So from here, I can say that I want the following function. I'm going to pick sine and tanh over and over again, and then I'm going to assign values as it. We can see that our functions are a sine of x over a and a tanh of x over a, and using these functions, we have values that are between -1 and 1, so our attractor isn't going to expand out like crazy. We're going to get something contained. So then the values I put in, which I found out a while ago, give like a really cool attractor. I don't know. I call it the Tiemansums twist because it looks like it's got some, I don't know, it looks like it's you took some shoelaces and you kind of like tangled them together. You'll see. So then I put in these values here, and then I could also add constants if I wanted to. And you can see here I have tons of other options. I have all these trig functions. I have the reciprocal function, so a over x. I have a over x squared, which are awesome. I can also put in 0 if I don't want one of these to be here. And if I also wanted to create an affine attractor in here, I also put x, which is cool because if I want an affine attractor to transform into a non-affine attractor, which I'll show you in a bit, I can do that. So I'm going to press next. I could also reset my functions if I wanted to, but we don't need to do that. So I'm going to press next. And same as before, it takes a little bit, but then it gives you this. Pretty cool. So I can zoom in on it, same as before, and you could kind of see that it's, I don't know, like lines curved and twisted into each other. It's awesome. And it tells you at the top what your coefficients are, the values you entered. Yeah. So let's see, what's next? Oh. It asked me if I want to know the dimension, if I want to create a subset, same as before, and then if I'm finished with the program. Cool. So the next thing I want to show you here is morphing, which is my favorite part of this program. So I can press generate here, and now you can see it's kind of similar to before, but now I have two sides. Actually, I'm going to start over with this little part because I want to be able to show you before I'm done recording. So I'm going to generate with 20,000 instead of 200,000 points for each picture because I want it to generate quickly. So I'm going to press generate, and I'm going to input my functions. I'm going to take the Sierpinski triangle and I'm going to morph it into that thing, which I called the Tiemansums twist. So I'm going to say x, 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 x for each of these because it is an affine attractor, which is the Sierpinski triangle. So I'll put that in here. And then as we saw before, I'll put in the 0.5 values for each of the Sierpinski triangle values. So 0.5, and then I'll put in all these zeros. Sorry about this. This is kind of the boring part. 0.25 and 0.433. Now on the right side, I'm going to put in the values for the attractor I just showed you before. And as you can see, clearly we have less options for the functions right now. Before I post this online, I will definitely make it so that you can scroll through. I just wanted it to be able to be contained in one window for now because a lot of the other functions I didn't end up using. But for the sake of this video, this is what it looks like. Okay, so then I need to put in my zeros. You can also see here that if I didn't, so I'm missing a value at the top here and I press next, it won't do anything. But then if you press 0 then and I press next page, you can see now it's kind of frozen. So I will go to your folder here, and I go to this folder. I called it I'm Learning because a long time ago when I first started making this, I was still learning how this works. So you can see here that it's generating these images. You can see it's replacing these morphing images that I already had before. So it's generating, it's at 59. And what I usually do is I just put these images, it'll generate as many as you specified. So I said 100, so it'll generate 100 images. If I click on them, I can scroll through and I can see that it is transforming into what I wanted it to. And there you go. And you could do it with more than just 20,000 points, and it'll just take a little bit longer, but it'll look nicer. Obviously, the more points you have, the nicer it'll look. So let's see what's next. So I generated those images, and now I can close this. I can do as many as I want. And now I have some other cool options. I can splice some together. I can make piecewise functions. Next thing I want to do, though, I want to show you a Mobius transformation. So I'm going to go back to 200,000 points because I'm just making one image. And I'm going to take my Mobius transformation, and it asks me what probability I want because I haven't fully finished this part yet. But, oops, 1/3. I'll press next page, and it brings me to this. Same as before. So I'll put in the sine values, sine tangent values. I'm going to make something funky. And I'll put in my values. I'm just going to put in some random values. It'll make me something cool. And do this. Put in zeros for the constants because, I don't know, I find whenever I'm making the trig functions, I just like to put zeros for the constants because it gives me something kind of cool looking. So anyways, I'll put in these values for the Mobius transformation, and then I'm going to press next. You can see here it explains how the Mobius restriction formulas work. I gave it at the bottom. And I also made a user manual for this if you want to know more in detail with the proofs and everything. But for now, this is how it works for inputting those values. I press next page, and same as usual, you just wait a second, and it makes the Mobius transformation. I think on the next one I make, though, I'm going to put a little bit less. Oh, I think I may have. I think I accidentally messed up. Oops. Give me a second here. Let's see. What did I do wrong? So if I press next page, so I'm going to say sine tangent. Actually, I'm going to make the same one as before because I want you guys to be able to see the difference between this and the Mobius transformation because it's super cool. So I put in the 0 values here. And then at the bottom, I'm going to press 0, 0, 0. And I'm just doing this randomly. There, you could put any values and they would look cool. Cool. So it should work now. Oh. Wait a second. I'm going to pause this video for now and go back to it. All right. Sorry about that. Okay. So here is what it would look like when you input those Mobius values. It takes the original one and it kind of manipulates it, it rotates it, it stretches it in different directions, and you get something like this. So yeah, so that is one thing. And there's this thing where it says, would you like to see an animation of the initial attractor being folded into its Mobius morph? That's pretty cool. Not for now. If you want to know the dimension, you can. If you want to create a subset, you can. And then it asks you if you're finished with the program, which we're not. So then you can do splices and morphs. You can do Mobius with a morph. You can do 3D graphs. And then you can also do these deterministically. You can do all of them. Is there anything I missed? So I did this thing called Morpheus, which is where you morph and use Mobius. I did this thing where I said Splorpheus, where you use splice and Mobius and morphing. And there's Splobius, which is splicing and Mobius without the morph. There's also 3D morphs, 3D splices. But for now, I'm just going to show you the 3D, and then I'm going to show you some examples of the morphing ones, and then we're going to call it quits. So I'm going to go to two functions, and I'm going to generate using equal probability. Oops. I'm going to say equal probability. And now you can see here that we have a whole bunch more to input because it has that extra dimension. So what I'm going to do here is I'm going to put in similar values, but again, it's going to be generating a 3D function. So let's see here. So it's sine, tanh, sine, tanh, sine, tanh, sine, tanh, sine. And I'm going to say 1, 2, 3, 4, 5, 6, 7, 8, 9 with no constants. And then I'm going to go down here and we say 9, 8, 7, 6, 5, 4, 3, 2, 1. I'm going to say 0, 0, 0 and go to the next page. And it'll give you this little error. Not sure why, but it always does. Anyways, there you go. There's your 3D plot. You can interact with it, but it's very slow and you can move it around. But yeah, so there's your 3D plot. So that is the program. Oh, wait a second. It'll also give you this smoother to interact with, but less pretty one on your browser. And then it asks you if you want to know the dimension, if you would like to create a subset, and then if you're finished with the program. So the last thing here is L systems, which is something I just added for fun. Literally did that today. Not fully sure how they work, but they're pretty cool. So you say the rules for what you want to do. So you say F is forward, you can say you can rotate it, and you can do all these things. And then the big blank window, which I haven't explained this entire time, is going to draw it. It's telling this little thing, it's called turtle, and it tells it which directions to go. So you can start with, say, F plus F plus F plus F. So I'm rotating and going forward, rotating and going forward. I'm starting by just going forward. I'm going to say how many times I want to do this. I'm going to say 8. I'm going to say what angle. I'm going to say 9. And the length I'm going to say is 10. I press enter. And you can see at the bottom here, it's drawing a ridiculous amount of tiny squares. But if, say, I change that angle to 34, and I change this length to 55, and I press enter, and it's drawing a circle now. I could say add another F here and change up the angles and then add in another F, and I can press enter and it's doing this now. Yeah, so this is still a work in progress, but I thought it was pretty cool. Yeah, let's see a couple other examples here. It'll keep doing this, that's okay. I can go to my nonaffine attractors, and here's an example of something I find really cool, is I made an animation where it's using a Mobius transformation, it's morphing, it's splicing, and it's splicing and Morpheus transformations. And I call it Morpheus to Splorpheus, which is just ridiculous. But anyways, it looks like this. And the color coding, that's just stuff to make it look pretty. So it's transforming from the one that I specified, the Tiemansums, and then turned it into the Sierpinski triangle with a Mobius transformation here. This is the splice and the Morbius transformation between the two. This is the Mobius transformation of the first one, and then it's just transforming into the first one. And it'll do that on repeat forever. Yeah, I have a whole bunch of these here, which I'll post online. But yeah, that's all it is really. Cool. All right, well, thanks for watching.